Okay, good morning, class. Right. So today we will continue on 4.2. Okay, so specific heat capacity. Right. So before I continue for 4.2, okay, so let me remind you. Okay, for those who still didn't submit, right? The word I give in GC. Okay, please turn in. Okay, and reminder, right? So I give you for the second exercise, I think I give until 8 p.m. today, right? So please submit, okay, because later on Saturday, okay, we have the extra class on Saturday. I will discuss all the exercise that I gave, okay, and then with the exercise that I gave before this, the one that we still not finish discuss, right? So we continue on that one. Okay, so let's see for 4.2, okay, specific heat capacity. Okay, so what you will learn in this subtopic, okay, that you have to know how to explain what is the heat capacity, okay, and also to define the specific heat capacity. Okay, so let's say you go to the beach, right? You go to the beach, and then when you touch the sand, okay, so when your feet touch the sand is feel hot. Okay, so but you go in the sea water is cold. Okay, so why is that? Okay, so the sun heats up the sand and also the sea water at the same period of time. Okay, but the sand is much hotter than the sea water. Okay, however, sand gets hot quickly and the sea water gets hot slowly. Okay, so this can be explained based on the concept of heat capacity. Okay, so different object they have a different heat capacity. So for this one, okay, since this the sand is become is hot faster than the water, right? So means the heat capacity for the sand is lower. So that's why it can heat up faster if you compare to the sea water. Okay, so sand has a low heat capacity and gets hot quickly. Okay, while the water that has a high heat capacity, so that's why the heat up slower than the sand. Okay, so let's go to the next one. Okay, so what does it mean by heat capacity and also the specific heat capacity? So we will see what's the difference between these two. Right, so the first one, activity one is to investigate a heat capacity. So they say if I have a pail of water, okay, and the swimming pool, okay, so I left for several hours, all right, so beside the pool. So which water is hotter? Okay, of course the water in the pail. Okay, so which water has a smaller mass? So of course the water in the pail. So which water needs to be exposed to the sunlight in the shorter time in order to raise its temperature by 100 degrees Celsius? So of course the water in the pail too. Okay. So which has the larger heat capacity? Water in the pail or water in the swimming pool? So of course water in the pool. Okay, because it takes longer to heat up, right? If you compare with the water in the pail. So make an inference about the relationship between heat capacity and also the temperature rise of a substance. So the higher the heat capacity, the lower the temperature rise. So as we compare here from the water in the pool and also water in the pail, okay, water in the pail heat up faster. So mean the heat capacity is lower. Okay, while the water in the pool, okay, it takes some time, okay, for it to be heated. Okay, so mean it has the larger heat capacity, right? So what does it mean actually by the heat capacity? So the quantity of heat, right, needed to raise the temperature of the object by 1 degree Celsius. Okay, so the quantity heat needed to raise the temperature of the object by 1 degree Celsius. So example, let's say if I say here, the heat capacity of the object A is 300, okay, 300 joule degree Celsius. So means if you want to raise the temperature, okay, so let's say if I draw it like this. So let's say if I have an object here, so object A. Okay, so let's say the initial temperature is 35 degrees Celsius. Okay, so and the heat capacity, okay, and then the heat capacity for the object is 300 joule degree Celsius negative 1. Okay, so they say this is the heat capacity. So what does it mean by heat capacity here? Okay, so to increase the object A from 35 to 36 degrees Celsius, it needs 300 joule of heat. Okay, so let's say if I give 300 joule of heat to the object A, we increase 1 degree Celsius, so it will become 36. So let's say if I give 600, so it will increase how much? It will increase 2 degrees Celsius. So 2 degrees Celsius, so 35 plus 2 is 37 degrees Celsius. So that's what does it mean by heat capacity. Okay, the amount of heat, okay, energy need, okay, to increase 1 degree Celsius for 1 degree Celsius. Okay, that one they don't have a 1 kg. So means they only need the quantity of heat needed to raise the temperature of the object by 1 degree Celsius. Okay. So the formula is C is equals to Q divided by, this is change in temperature. Okay. Theta. Okay. So C is equals to Q over change in temperature. So this is the formula. Alright. So any question for the heat capacity? Okay, the amount of heat needed to increase 1 degree Celsius for the object. Okay, so let's say 35 go to 36. So how much energy need to be increased, to be given, so it can increase from 35 to 36. Okay, any question you want to ask about the heat capacity? No. Is it okay? Can you understand for the heat capacity? Okay, so to investigate the heat capacity. So when a 2000 joule of heat is supplied to object X and Y, object X experiences a rise in temperature of 1 degree Celsius and object Y by 2 degrees Celsius. So what is the heat capacity of object X? Okay, so we use the formula C is equals to Q divided by change in temperature. Okay, so I give example for object X. So object X, okay, so the C is equals to Q divided by change in temperature. So you can see they give 200 joule here. So mean this is the quantity of heat supply. So that is 2000, right? And then the change in temperature for object X is 1 degree Celsius, right? So divide by 1. So you will get 200 joule, alright, degree Celsius negative 1. Okay, so that's the formula. Okay, so C divided by Q. Q is what? Q is the amount of heat. So amount of heat, so there is a heat is a energy, right? So amount of heat the unit must be in joule. So 2000, so you divide by the change of temperature already given that it experienced the rise of temperature is 1. So means the change of temperature is 1 degree. Okay, so you just divide, you will get 2000, sorry. So thank you. Thank you for reminding me. I forgot to add another one. So 2000 J degree Celsius negative 1. So how about object Y? Okay, can you calculate for object Y? 1000. Okay, so 1000, so 2000 divided by 2 because the change of temperature is 2 degrees Celsius. So you will get 1000 J degrees Celsius negative 1. Alright, so you compare the heat capacity here. So the heat capacity for object X is 2000 while the object Y is 1000. So you can see for those who has the heat capacity lower, right? So object Y, they have a lower heat capacity, right? So you can see it increase the temperature more than X. Okay, so means the lower the heat capacity, the higher the change in temperature. Okay, so if we compare like this one object Y 1000 and this one object X is 2000. Okay, so for the heat capacity Y 1000, you can see it increase 2 degrees Celsius. Okay, for object X, even you give 2000 joule, okay, the same amount of energy you give, but it can only increase 1 degree Celsius. Okay, so that means the X has the high heat capacity than the object Y. So that's why the object Y, okay, can increase faster the temperature if you compare to X because of the heat capacity here. Okay, for the Y, they have the lower heat capacity, so it will have the higher rise in temperature. Okay, the rise in temperature in X is lower than Y because of the heat capacity is higher. Okay, so which object is hotter? Object Y. Okay, so it's just example like this. If I have the two object A and B, okay, so let's say the heat capacity here is 200 joule, right? And this one is 100 joule negative, that degree Celsius negative 1. Okay, so let's say if I give 400 joule of energy. Okay, so let's say if I give 400 joule of energy, so what is the temperature increase here? If I give 400 joule, if I give 400 joule to the object A, so what is the temperature? What is the how much is the rise in the rise in the temperature? 2 degree, right? Because 200, if you give 200, it will increase 1 degree Celsius. So if you give 400, it will increase 2 degrees Celsius. Okay, so if you give 200 joule, it will increase 1 degree Celsius. So let's say if teacher give 400 joule, so it will increase 2 degrees Celsius. Okay, for this one, for object B, if I give 400 joule, yes. So if 100 joule, it will increase 1 degree Celsius. So if I give 400 joule, it will increase 4 degrees Celsius. So you can see here, the lower the heat capacity, you can see the higher the increase in temperature if you compare with A. Okay, so can you understand? Anything you want to ask teacher? Raja and Asher, please tell the what project you want to do. Okay, so the still the last day I give is tomorrow. Okay, so please think. Okay, so object with high heat capacity heats up slowly. Okay, so this one same like the one that I gave just now. Okay, so for 900 joule, okay, it will increase 1 degree Celsius. But if you want to heat up 2 kilograms, so you will need 1800 joule of heat. Okay. Okay, so object A and B are made from aluminium but have different heat capacity because different mass. Okay, so the higher the mass, of course, it will be the higher the energy you need, alright, to heat up the aluminium. Okay, so object A needs 1 kg, okay, and object A of mass 1 kg needs 900 joule of heat to rise up temperature by 1 degree Celsius. While object B, okay, has mass 2 kg, it will need 1800. So you have to double up. Okay, because this one kg is 900 joule. So if 2 kg, it need 1800. So you just multiply by 2. So mean you can see here if you have a different mass, it will be different heat capacity. Okay, so the heat capacity for B is bigger than heat capacity of A. So heat capacity for an object is higher when its mass increase, right? So is okay. So is this is the same, right? So let's say if I have object C and object D, okay, object C and object D, okay, object C and object E. So let's say for 1 kg of object C, okay, for 1 kg of object C, we need 200 joule. Okay, so let's say for 2 kg, we need 400 joule. So you will just double up. So this one to show that if the mass is different, okay, the speed, if the mass is different, the heat capacity also will be different. Okay, so let's try to do this one. Okay, try to answer for A, B, and C. Okay, so let me ask Avinash. So which kettle boils for longer time? P or Q? So Q. Okay, correct. So Raja, so which kettle has larger quantity of heat? P. Okay. Which kettle has a larger quantity of heat? Is it P? It's Q. Because Q has a higher mass. So higher mass, high heat capacity. Okay. So we just doing this now, right? If you 2 kg is as 1,800. Okay. And which kettle has a larger heat capacity? Of course, Q, because it has a higher mass. So higher mass means you have to have higher heat capacity. Right. So what you make an inference about the relationship between the heat capacity and the mass of substance. Okay. So the higher the heat capacity, the higher the mass. Okay. And what factor that affect the heat capacity? The mass. Okay. And also the rise of the temperature and the material of the substance. So what material that you use? If aluminium, then it's different. If copper, then it's different. Okay, so this one, investigate the specific heat capacity. Okay, so different quantity of heat is needed to raise the temperature by 1 degree Celsius for two objects A and C, even though their masses are equal. Okay, so just now we ignore the mass, right? We ignore the mass. We just take the quantity of heat and also the change in temperature. Okay, but for the specific heat capacity, we consider the mass here. So the mass of the two objects that we compare must be the same value. Okay, so the different quantity of heat is needed to raise the temperature by 1 degree Celsius for two objects A and B, even though their masses are equal. So this is because two objects are made from different material. So different substance has different specific heat capacity. So what is the difference between the heat capacity just now? So the heat capacity you use to measure material that is same material. So both is water, right? But for the specific heat capacity, okay, we used to measure the different substance, different material, and also the mass must be same. Okay, so for the heat capacity, same material. Okay, for the specific heat capacity, different material. Alright, and for this heat capacity, same material, and also it can be in different mass. Okay, for the specific heat capacity, different material, same mass. So it's opposite. Alright. So what is that mean by so which substance needs large amount of heat to raise temperature by 1 degree Celsius? Okay, so you can see here rise of temperature by 1 degree Celsius. Okay, for aluminium they need 900 joule. Okay, for the plumbum, okay, PB is a plumbum, so it only need 130 joule of heat, okay, to rise the temperature 1 degree Celsius. So of course, the answer should be aluminium. So you can see if you want to raise the 1 degree Celsius of aluminium, is need 900 joule. But if you compare to plumbum, it's only need 130. So the answer is aluminium. Okay, so plumbum heat up faster than aluminium because it need less heat to raise temperature 1 degree Celsius. So let's see if I give 900 joule, okay, 900 joule to the plumbum. Okay, so if I give 900 joule to the plumbum, okay, plumbum only need 130 joule to increase 1 degree Celsius. Okay, so but if I give 900 joule to the plumbum, so it will increase around like 7 degrees Celsius, almost 7 degrees Celsius increase. Okay, that is for plumbum. But for aluminium, if you give 900 joule, it will be like almost only 1 degree Celsius increase. Okay, but if you give the same amount to the plumbum, same amount of heat to the plumbum, it will increase almost 7. Yes, 6.92. Right. So you can see here if the less heat needed, okay, so it will increase more higher. So let's say here plumbum heat faster than aluminium because it need less heat to raise the temperature 1 degree Celsius. Okay, so that is the specific heat capacity. So remember the heat capacity we compare same material, water with water, okay, but different mass. Okay, but for the specific heat capacity, we compare the different material, but the mass must be same. So usually it's 1 kg. Okay, 1 kg of substance. So what does it mean? What does it mean by 1 kg of plumbum needs 130 joule of heat and 1 kg of aluminium needs 900 joule of heat to raise the temperature by 1 degree Celsius? So I just explained just now, you give 900 joule to aluminium, it's increase 1. Okay, if you give 130 joule to the plumber, it increase 1. But let's say if you give 900 joule to the plumbum, it will increase almost 7 degrees Celsius. So it means plumbum heat up faster than the aluminium. Okay, definition of the specific heat capacity. So the meaning is only the difference is a 1 kg. Okay, so the quantity of heat needed to raise the temperature of 1 kg of mass of substance by 1 degree Celsius. Okay, how many energy that you need to increase, okay, for 1 kg of, let's say, of block, of metal block, okay, for the metal block to increase only 1 degree Celsius. So how much energy that you need? So let's say if I have object C, okay, so the specific heat capacity is 450 J kg negative 1 degree Celsius negative 1. So this is the unit for specific heat capacity. Okay, so what does it mean by 450 here? So it means the object C needs 450 joule of energy, okay, to increase 1 degree Celsius, okay, by the mass is 1 kg. Okay, with the mass is 1 kg. Okay, So that's the meaning of the specific heat capacity. So it means the specific, why we put it as specific, because it must, the kg must be in 1 kg. So just now for the heat capacity, the mass can be anything, right? But for the specific, there must be 1 kg. The metal or the object must be, the mass is 1 kg. Okay, and then the amount of heat to increase that 1 kg of an object uh, in 1 degree Celsius. Okay, how much energy that you will give to the object. So that is the specific heat capacity. Okay, so for this one, they say if I want to, for C, for the object C that I just gave just now, so if I want to increase the object C in 1 degree Celsius, okay, and remember the object C must, the mass must be 1 kg, so I need to give 450 joule of heat energy to object C so it can increase 1 degree Celsius. Right? So this is the formula. C is equals to Q divided by M theta, or I like to use Q is equals to MC theta. So what is the Q? Q is the heat. What is the quantity heat being given? Okay, you apply to the object. Okay, and the unit, later we see the unit. Okay, M is the mass, theta is the rise of temperature. So the final temperature minus with the initial temperature, and C is the specific heat capacity. So the unit of heat is joule, the mass must be in kg, the rise of temperature must be degree Celsius, and the specific heat capacity unit must be J kg negative 1 degree Celsius power of negative 1. Okay, so this is the formula for specific heat capacity. It's different from just now, that is Q divided by change of temperature, right? For heat capacity, they don't have mass here. Okay, for the for the specific heat capacity, they have a mass here. So remember, theta is the rise of temperature. So you have to minus the final temperature with the initial temperature. Okay, so this is the formula. So remember, heat capacity, amount of heat energy required to raise 1 degree Celsius. Okay, they don't have kg inside of it. Okay, inside of the meaning. But for the specific heat capacity, the amount of heat, alright, required to increase 1 degree Celsius for 1 kg of substance. Okay, so they have word 1 kg there. Okay, so this is the formula. Okay, now I want you to write the meaning, okay, for each sentence of this. Okay, for number 1 and number 2. Okay, remember just now that I gave this example, right? 450 joule kg negative 1. I said 450 joule needed to increase. So I want you to give the meaning, okay? What is the mean by 900 joule kg negative 1 degree Celsius negative 1? Okay, number 1 and number 2. Anything you want to ask, teacher? Specific heat capacity, heat capacity. Okay, so I would like to call Nirupa for number 1. Okay. Nirupa, the quantity of heat needed. Okay, I want you to answer in the also 900 joule. So what is the function of 900 joule here? You have to state the 900 joule also in your sentence. You have to state the 900 joule also in your sentence. The quantity of heat that needed, the quantity of heat needed to increase the temperature of. Okay, you missing one very important word there. 1 kg. I told you specific heat capacity must have 1 kg. Okay, number 2 I will ask Sajif. You try number 2, Sajif.
4,200 joule of
Mm.
energy is needed to rise the temperature of 1 kilogram of water by 1 Celsius.
Yes, very good. That's the answer. Okay, so Nirupa, that's how you want to answer for question number 1. You have to state the how much amount energy that you need to increase. So the quantity of heat needed to increase the temperature of water with mass of 1 kg by 1 degree Celsius is 4,200 joule. Yes, also can. Okay, so are you clear, Nirupa? So let me give you the answer. So 900 joule, so means the amount 900 joule of energy of heat energy needed to increase 1 degree Celsius for 1 kg of aluminium. Okay, so this is the answer. You have to include the value also in your sentence, right? So and for this one, okay, so same. Okay, so the amount of heat needed to increase, so you have to change it to the value. So 900 joule of heat energy is used to increase 1 degree Celsius, okay, for 1 kg aluminium. Are you clear, Nirupa? Because this one sometimes they ask you in paper 1, okay, the objective part. Okay, they ask you what is the meaning of 900 kg negative 1. Okay, so let's say for this one, okay, a metal has mass 2 kg. Okay, so calculate the amount of heat that must be transferred to the metal to raise the temperature from 30 degrees Celsius to 70. So we take out what the formula for what is the info given here. So the mass is 2 kg. Okay, and then they ask you to calculate the amount of heat. So amount of heat is Q. Right, and the theta is the change of temperature, so 70 minus 30, 40. Okay, 40, right? Okay, and then the C is the 500 joule. Okay, so next you use the formula MC theta. M is 2, C is 500, theta is 40. So you will get 40,000 joule. Okay, so that's how you want to use the formula. Okay, for this one, alright, so how many joules energy are required to raise the temperature of 100 joule, 100 gram of coal from 20 degrees Celsius to 100 degrees Celsius? Okay, so same formula. Okay, but remember the mass here is in gram. Okay, so you have to change to kg. Because of what? Because of the gold here also they use a kg here. So you need to change to kg, so it becomes same. Then after that you can use the formula. So 0.1, okay, and then the C already given, okay, 129, and then the theta is the change of temperature. So the final temperature is 100, the initial temperature is 20. So you just minus, you will get 80. Okay, and then you just substitute in the formula, then you just calculate, right? So what's the application of the specific heat capacity? Okay, so the actually this one, if you want to make a pan, right, or the frying pan. Okay, so this one is the pot. So low specific heat capacity. So the pot becomes hot very quickly. So at the base, okay, at the base you have to put the material that heat up faster. So for this one, we use the low specific heat capacity so it can heat up faster. Okay, and then also at the bottom one, at the copper base here, at the base here, so it must have the high density so it can be stable, so it will not move, okay, move around like that. So the heavier base ensure that the pot is stable and will not topple over easily. Okay, how about the body? So the body also must be in aluminium, so must have the low specific heat capacity too, so it can heat up faster. Okay, but for the handle, so the handle is a very different story because you don't want, when you hold the handle, it's hot, right? So you have to choose the one that has a high specific heat capacity. So it will not heat up faster, or you can say it's a poor heat conductor. So it will not heat up easily. Okay, so this is the function that you learn with the specific heat capacity. So low specific heat capacity, the temperature increase faster. High specific heat capacity, it will not heat up faster, it will heat up slowly. Okay, so it just same like the conductor and also the insulator. The conductor, usually we already know, if you expose it to the heat, it will heat up faster. Right, so means the conductor has the low specific heat capacity. For the insulator, okay, they have the high specific heat capacity, so that's why they heat up slowly, right? So that is actually a connection between the insulator and also the conductor. Okay, so the sea breeze, right? So this one is actually occur at during the daytime. Okay, so sometimes they ask you to explain, right? To explain what happened during the sea breeze. Okay, so the sea breeze is actually about the specific heat capacity, using the specific heat capacity. So what happened here? Okay, so the land, okay, the land has the low specific heat capacity. So if low specific heat capacity means it heat up faster, okay, compared to the sea. Okay, it heat up faster. Okay, and then when it heat up, okay, you have to know the hot air, the density of the hot air is less than the cold air. So when the density is less, so it's easy for the hot air to go up. Okay, so easy for the hot air to go up because of the density of the hot air is lower. So the density of the hot air is lower, so it will rise up. Okay, and then from the sea there is a cold air. If you compare with the land, the sea is cold air, so cold air will move to the sea. Okay, so the cold air will move to the sea. So that's why, okay, you can see during the time at daytime, you go to the beach, you can see the wind is come from the sea to the land. Okay, during the daytime, right? So this is the explanation. Okay. Alright, so the opposite one is the land breeze. So what happened during the night time? Okay. Okay, so during the night, alright, so this one it's different, right? Since the land has a low specific heat capacity, okay, So this one we change to C. So we discuss about C. So the C is uh, is hot during oh, sorry. Okay, the C is hot during during night compare to land. Okay, because C has higher specific heat capacity. Alright. So since C has a higher specific heat capacity, so it will not easy for the C to cool down. Okay. So you just remember for those objects that has a lower specific heat capacity, it heat up faster and also it is cool down faster. Okay, heat up faster, cool down faster. Okay, for the object that has a high specific heat capacity, it will take some time to heat up, okay, and also it will take some time to cool down. Okay, so that's why for the C, it's still hot even at daytime because it has a high specific capacity. It takes time for it to cool down. So if you compare, means the C has has a high temperature. So high temperature means the density of air, okay, the density of air, okay, at the sea, the density of hot air at the sea will rise up. Okay, so the cool air from the land will go to the sea. Okay, so this is how you explain for the 4 marks. Okay, 4 marks question, the explanation, that question number 9 or number 10, the essay part. Okay, section B and section C, paper 2. Okay, so if they ask you how to explain how does the sea breeze occur or land breeze occur, so you need to answer like this. Okay, so you need to mention about the specific heat capacity. During the daytime, the specific heat capacity of land is lower, so it will heat up faster. Okay, so the density of the hot air in the land will rise up. The cool air from the sea will go to the land. Okay, so it's a sea breeze. All right, for the land breeze, okay, so because sea has the high specific capacity, so it will cool down slowly, right? So mean it's still hot. Okay, so the density of air, okay, on the sea will rise up. Okay, and the cool air from the land will goes to the sea, so it will become land breeze. Okay, so every object that has a low specific heat capacity, so it will heat up faster, cool down faster. Okay, so cooling system of car engine. So for this one, we use a water. Why we use a water? Because water has the high specific heat capacity. So means it's not easy for the water to rise up the temperature. So it can absorb more heat. Okay. So let's say if you put the alcohol is a very low specific capacity. So let's say if you start your engine, then let's say for the water is 4,200. Okay, that is the specific heat capacity for water. Okay, there is a specific heat for water. Right, so let's say if I give water 4,200 joule of energy, so it will rise only 1 degree Celsius. So for alcohol, so depend on the type of the alcohol. So let's say 180 J/kg negative 1 degree Celsius negative 1. So what will happen here? So let's say if I give 180 degrees joule 180 joule energy to the alcohol. So it's already 1 degree Celsius. But if I give 4,100, you can imagine, okay, how much that the temperature will increase. So that's why we use the water, because it can contain high specific heat capacity. So it can absorb more heat, and it's hard for the water to rise up the temperature. Okay. So the first one is because the high boiling point is not easy to change to gas easily. So high specific heat capacity, so it can absorb a lot of heat. Okay. So if let's say 4,200, it absorb, then it can rise to 1 degree Celsius. So that's a lot. Okay, 4,200. Okay, it's abundant, economical. So actually, water is can get anywhere, right? So it's cheaper and save costs. Okay, so this is the water pump, right? So you have to know, all right? So this is the fan. Okay, so this is the mechanism. Okay, how does it cool down the engine? Okay, so the first one, the heat is released to the cooler air that flows to the cooling fans. Okay, and then you pump the water into the engine block. Okay, and then the hot water flows to the radiator. Okay, and then before that, the heat produced, okay, by the engine is absorbed by the water. So then the hot water will flows to the radiator. Okay, so then after that it will be released, okay, through the cooling fans. All right, so this is the principle, working principle for the engine. Okay, so but what you have to know is actually this one only. Okay, why we use a water inside the car engine. Okay, the next one. Okay, so heat energy cannot be created. So this one is actually the principal conservation of energy, right? So you cannot create energy, you cannot destroy energy. What can you do is only you can change the form of energy. So heat energy cannot be created. So however, electrical potential and kinetic energy can be converted to heat energy. So I take one example like electrical energy. So using your kettle, okay? So when you heat up your kettle, of course you use the electrical energy. So that electrical energy, the formula is PT, okay? So PT, right? And then when you change to the heat, okay? So what is the formula for the heat energy? Is MC theta. So remember I said the energy cannot be destroyed. So you just assume that how much the electrical energy, how much that we supply the electrical energy, so that is the heat energy that will be produced. So there will be no heat loss to the surrounding, there will be no energy loss to the surrounding. Okay, so that's why we get PT is equals to empty theta. We assume the electrical energy that we give to the kettle, okay, is actually equals to the heat energy that will be produced to heat up the water. So that means there is no heat loss or there will be no energy loss to the surrounding. So this is PT is equals to MC theta. Then sometimes they will ask you, what is the principle you're using here, right? What is the principle you use here? PT is equals to MC theta. So this is what? This is the principle conservation of energy. So this is the principle that we use. Okay, we assume that electrical energy is equals to heat energy. Okay, so and then another one, they say it's the object fall from high position. Okay, they say you just throw an object from the fourth floor. Okay, okay, and then you throw that it have a potential energy. Okay, so after that you change to heat energy, that is mgh. Your potential energy here, the formula is mgh, so equal to the heat energy mc theta. So that's the formula. So again we use the principal conservation of energy. So kinetic energy, moving object stop due to friction. So let's say the object is moving, okay, suddenly it stop because of the friction. So you know the friction will produce the heat energy, right? So the movement, when the object move, it has a kinetic energy. So we just assumed here the kinetic energy that when the object is moved, okay, is actually equals to the heat energy that produced, okay, due to friction. Okay, so that is the formula, okay, or the formula that maybe you can use, okay, when you calculate the heat energy. Okay, so try to answer number one first. Remember, E is equals to PT. What is P? P is a power. Okay, and it's in watt. Right? Time is what? Time is time, and it must be in second. So for this one, you have to change minutes to second first. Okay, did you finish it? Okay, Eugene for 1A, and for 1B, Lakshmi. Eugene. Wait, no, wrong. 500 joule. Is it correct? I already. Time must be in second. Okay, if you use minute, you cannot use joule. Lakshmi, the 95.24. Okay, so let's see whether it's correct or not. Eugene, the 300,000. Okay, so let's see. For A, okay, we use E is equals to PT. So it said here an electric kettle is rated 1000 watt. Okay, so means the kettle needs 1000 watt, okay, a power. Okay, and then it asks you to calculate the energy, right? The heat quantity of heat generated in 5 minutes. Teacher, heat energy, the formula of heat energy is not MC theta. Yes, it's MC theta. Okay, but remember I told you the electrical energy is actually equals to MC theta. If you want to use the MC theta, we don't have any info. Okay, how about the mass? How about the theta, the increase of temperature there? So it's not stated in the question. So what you can assume here that is PT is equals to MC theta. So we just take E is equals to PT. So we calculate that one, and actually that one is also same as the heat energy. Okay, so P is a 1000, theta is 60 times 5, right? So 1000 times 300, so you will get 3123123, so you will get 3 3 right? So 1 2 3, so this one is 3, so I just change to standard form, it's much easier. 4, 5, 6. So 3 times 10 power of 6 joule. Okay. So everyone, you get the answer for this one. 3 times 10 power of 6. Okay. So B. So it said here, the rise of the temperature of 750 gram of water if the electric kettle is switched on for 5 minutes. Okay, so you need to calculate the rise of temperature. Means you need to calculate theta here. Okay, so I already told you just now, PT is equals to MC theta. How much the electrical energy that we give, that is actually equals to the heat energy. So now we already have PT, right? So we can use this formula. PT is equals to MC theta. PT we already calculate, that is 3 times 10 power of 6. Okay, and then the mass change to kg first, 0.75. Okay, C is 4,200, the specific heat capacity of water, 4,200, and the theta is the change of temperature that you need to find. Okay, so let me find my calculator. Okay, 0.75 times 4,200, and then 3 exponent 6 divided by. So you get 90. Wait for a moment. So what is the temperature? Wait, 1000 times 300, right? Oh my god. This one is 300. Sorry. So 3 times exponent 5. Why you didn't say? Just now all of you got 3 exponent 6 also. 3 exponent 5 divided with 0.75, 4,200. So 3 exponent 5 divided by answer, you will get 95.24. Is it correct? 95.24 degrees Celsius. Okay, good, Lakshmi. Okay, so 95.424 degrees Celsius. Okay, so this one is actually 60 times 5 is 300, not 3,000. Okay, so correct. So for this one, try. Okay, so for this one, Sajif, you want to try for this one, number two? So it say here the 200 gram of water, okay, with a temperature of 40 degrees Celsius, and you mix up with the 800 gram of boiling water. So boiling water is, what is the temperature for the boiling water? So this one is 100 degrees Celsius. So if there is no heat loss to the surrounding, what is the final temperature when the mixture of the water achieves thermal equilibrium? Anyone? Or maybe anyone already got the answer? So what is the formula that you use here? 88 degrees Celsius, okay? Ketiga got 88. Asha, Abi, Rami, Michael, Avinash, Tisha, Raja, Rindya, Sharanya, Tava, 85. Not sure what formula to use, teacher, okay? 88, 85, same. We can got 85. Okay. So let's read the question here. So when you add for 40 degrees Celsius, all right, the temperature of water that is 40 degrees Celsius, you add with the 800 gram, that is 100 degrees Celsius. So we just learned yesterday, right, about the thermal equilibrium. So the heat we transfer from the hot object to cold object. So means the heat we transfer from the 100 degrees Celsius of water to the 40 degrees Celsius of water. Okay. So it's already give you the info that it said no heat loss to the surrounding. So what we can assume here, okay. So which one lost the heat? Which one we lost the heat? The 100 degrees Celsius or the 40 degrees Celsius? Which one we lost the heat? 100 degrees Celsius. Okay. So the formula that you need to use is actually, we assume that the heat release is equals to heat absorbed. So you told me just now the heat release is 100 degrees Celsius. The temperature that have the 100 the water that have the 100 degrees Celsius. Okay, so that one the heat will be released if we lost the heat. So if we lost mean the heat release lah. Okay, so how about the heat absorbed? So the one that we absorb the heat is 40 degrees Celsius. Okay, so we assume that the amount of heat release is actually equals to the amount of heat absorbed, because it's already mentioned here there is no heat loss. Okay, so there will be no heat loss here. No heat loss. Okay, so heat release. So what is the formula for heat? MC theta, the energy of heat. So this one also same, MC theta. Okay, so the mass here, is 200 gram. Okay, so 200 gram. Okay, you change to kg is heat release is 100 degrees Celsius, right? So the mass is 800. Okay, so you change to kg first, 0.8. Okay, so C you can just ignore the C because both of it using the same material, both of it using water. So we just ignore the C there. Okay, and the theta. So you just told me just now the heat release. So the heat release meant this. The heat release, so the temperature will decrease, right? So when decrease is 100 minus theta. Yes, because the heat will be released. So the temperature will decrease. So it minus. Okay, for the heat absorbed, so the mass is 0.2. Okay, again C you just ignore because they use the same material. Okay, and then the theta here, the 40 degrees Celsius will increase. So means the final temperature is bigger than the initial temperature. And you want to find the final temperature. So there is theta minus 40. Can you understand? Can you understand? Yes. Nirupa, Rashmi, Sharanya, can you understand? You want me to explain again? We can. You want me to explain again? Oh, okay. Okay, sure. All right. So I explain again. Hmm. How do I do this one? Okay, never mind. Okay, so from here it said that 200 gram of water with a temperature of 40 gram, 40 degrees Celsius, alright, is mixed with the water of the boiling water that has a mass of 800 gram. So we assume there is no heat loss to the surrounding. So what is the final temperature when the mixture of water achieves thermal equilibrium? So means thermal equilibrium means both of it will have the same final temperature, right? Okay, so what we assume here, since it said there is no heat to the surrounding and no heat loss to the surrounding. Okay, so we assume that the heat absorbed is equals to the heat release. Okay, so for this one, for the 100 degrees Celsius, okay, 100 degrees Celsius here, you know the boiling point is 100 degrees Celsius and this one is 40 degrees Celsius. So you know the heat transferred from the hot object to the cold object. So means the heat from the water that have the 100 degrees Celsius we transfer to the water that has a 40 degrees Celsius. So which one we lost the heat? Of course, the boiling water we lost the heat, while the 40 degrees Celsius we receive the heat from the boiling water. Okay. So I make equation. So the heat release is equals to the heat absorbed. Okay, so what does it mean by here? The heat released by the water but the heat released by the boiling water is actually equal to the heat that absorbed by the 40 degrees Celsius of water. Okay, so they just give like 100 degrees Celsius give energy to the heat to the 40 degrees Celsius. So the amount of heat is same. Right? So this why is there anything you want to ask until this one? How I get the equation here? Heat release equals to heat absorbed. Is it okay? Farah, Sajif. Okay. So means the amount of heat released by the boiling water, okay, is the same amount that heat absorbed by the 40 degrees Celsius of water. So it will not lost to the surrounding. How many that you give, that is how many I will accept. Alright. Okay, so and then after that we use the formula. So what is the formula of heat here? There is mc theta. Mc theta is equals to mc theta. Okay, the heat release. So the heat release is the one that boiling water, right? So the one that 100 degrees Celsius. So what is the mass of the boiling water is 800 gram. So you change the mass to kg first, so 0.8. Okay, the C you can just ignore. Even so, you know when I change here, it will change to divide by C, right? So you can just cut it off. Okay, so you will left until only theta here. So I cut it off. So theta. So theta here 100 degrees Celsius. So the 100 degrees Celsius we lost energy. So when you lost energy, of course the temperature will decrease. Okay, so 100 minus theta because it will decrease, right? So 100 minus. So minus theta, so you can see the temperature is decreasing. Okay, and then for the heat absorb, okay, so the mass here, if I'm not mistaken, is 200 gram. So means you have to change to kg 0.2. That is the mass. So but this one, the 40 degrees Celsius, the temperature will increase, right? Because it receives heat from the boiling water. So it will increase. So should be theta minus 40. Okay, means the final temperature is higher than the initial temperature, right? Because theta is final minus initial. So this one, final temperature you want to find minus initial temperature 40. Okay, so until that, can you understand? Sajif, Farah, caranya, are you okay? Okay, so after that, what you have to do, you have to expand it. Okay, so 0.8 times 100 and then after that 0.8 times theta. Okay, so try to expand it and find the value of theta here. Eight teacher. Okay, so 0.8 times 100, you will get 80, right? So 80 minus 0.8 theta. Okay, just expand like that. So this one is 0.2 theta minus 0.2 times 40, you will get 8. Okay, so this one I change 0.2 theta plus 0.8 theta. This one 80 plus 8. So this one I got 1, right? 1 degree, 1 theta is equals to 88. So theta is 88 degrees Celsius. Okay, correct. Did you get the answer 88? Eugene, are you okay? Okay, so let's check whether it's correct. Yes, 88. So you see the equation, right? So the one that absorb, the one that release, the temperature will decrease. So you have to minus 100 minus theta. Okay, for the one that absorb, the temperature will increase. So theta minus 40. The final temperature is higher, right? So the final minus the initial. Okay. Okay, so for the next question, so how long does it take for an emission heater of 12 watt to raise the temperature of 200 gram water by 5 degrees Celsius? So you just take out what's the info given here first, then you see what's the formula that you can use. So this one, it give you the power here. Okay, and then they give you the mass and also the rise of temperature, the change of temperature here. And so they give you already C. Right? So can I ask Avinash, so what is the formula that you should use here? Not sure again, teacher. Okay. So did you already take out what's the info that given in the question? Avinash, for the question before this, did you understand for this one? Slightly. Okay, never mind. Do you have a class after this? What class after this? Okay, okay. Right, so I cannot ask you to stay for a while. Um, Never mind. I will text you. Okay, for this one, let's take out first what is the info given here. So the power is 12 watt. Okay, and it's used to rise the temperature for mass 200 gram. So mass is 0.2. I just changed to kg. Okay, and then the temperature rise is 5, sorry, the temperature rise is 5 degrees Celsius. Okay, and the C already given 4,200. Okay, and they ask you to find the T here. So what is the formula that you can use? PT is equals to MC theta. Okay, so the power is 12. All right, the time you need to find. Okay, and the mass is 0.2. The C is 4,200 and theta is 5. So find for me the T. 350 seconds. Okay, so just leave it like that. Don't change to minute. Okay, unless the question asks you to change. Okay, just leave it in second. Okay, good. All right. Oh, sorry. Okay, for number 4. So for number 4, it says a lead bullet, okay, moving at the velocity of 200 meter per second, hits a sandbag. Okay, so the temperature of the lead bullet rises by 50 degrees Celsius. So assuming that all the kinetic energy of the bullet is converted into heat energy that heats up the bullet, calculate the specific heat capacity of the bullet. Okay, so for this one, I would like to ask, Sharanya, what is the principle that we use here? When we said that all the kinetic energy converted to the heat energy. What is the principle that we use here? If you hear what I explained about the PT is equals to MC theta, all of that, I said what is the principle that we're using here? Sharanya. Yes, very good. So for this one, we assume the kinetic energy. So what is the formula for kinetic energy? Half mv squared. So it changed to what? Heat energy. What is the formula for heat energy? Mc theta. Yes, very good. So and then after that, you just use the formula here. But the mass is not given, right? So again, you use the same material, right? Both of it is bullet, so we can just ignore. Okay, if not, we have changed here also, we have can just cut it off. Okay, so it will left half v square c theta. Okay, so v is 200 square, c is c you need to find, theta is 50. So you say it rise 50 degrees Celsius. So you just find the C here. The C is 400. Is it correct? Others do you get 400? Yeah, 400 J kg negative 1 degree Celsius negative 1. Okay, good. Okay, so this is the last one. So I just explained for this one. So this one, so it said here that the lead ball of mass 320 gram is dropped from the height. Okay, 12 meters. So the collision between the ball and the ground is completely inelastic. So inelastic mean after it fall, it will stick to the ground. Okay, so assuming all of the energy of the ball goes into heating it, so calculate the change in temperature. So what does the energy that that being possessed by the lead ball when it has when it's at the height of the 12 meter? So it has a potential energy. So if you said like this one is wrong. So you have to mention gravitational potential energy. If you put the potential energy is wrong because potential energy got two type of energy, gravitational and elastic, right? So you have to put gravitational potential energy is equals to heat. Okay, so the formula is mgh. This one you already learned in form 3. So mgh is equals to mc theta. So again, right, we just ignore. Okay, so m is the mass here. So mass is should be 0.32, right? Okay, but maybe because they use the same, so just cut it off. So they just didn't put the mass here. So the mass here is 0.32, okay? So should be like this, 0.32 times G is 9.81, okay? And then the H is 12, okay? And then MC theta, M is 0.32, okay? And then the C is 128 times theta, okay? If the mass is given, you have to put in your equation, okay? Unless it's not given, just number question number 4 is not given, right? So you just can ignore the mass, okay? But this one, if they give, you need to put it, okay? Don't just do it like this. This one is wrong, okay? So we got the, what is the answer? Is it correct? 0.9375. Is it correct? Because now we conclude the. Did you got the same answer? 9.19. Teacher 0.92 times 9.81. 0. Others, did you got the same answer? Yeah, I got 9.81 times 12, right? So I got 37.67. 0.32 times 128. So 37.67 divide by answer. You got zero. I got 0.9196 at that. So yeah, so I got 0.92. Okay, 0.9197 because I round off. So you give only 3 decimal points. So I got 0.92. Okay, 0.92 degrees Celsius. So you see it's quite different. Okay, so please conclude in the, if they're given, you have to use. If not given, then you can just ignore. But make sure they compare the same material, the same object. Okay. Alright, so before I stop, okay, so I just summarize what we learned today. So specific heat capacity, heat capacity is the amount of heat, okay, energy that we need to raise 1 degree Celsius, okay, of an object, okay, and then for the specific heat capacity, the amount of heat need to raise 1 degree Celsius for 1 kg of an object. Okay, and then you have to know that low specific heat capacity, it will heat up faster. Okay, and the high specific heat capacity, it will heat up slowly. Okay, and then another one you already learned, okay, how to calculate the heat energy. We use the formula Q is equals to mc theta. That is the heat energy formula. Okay, and then they say you know by using the principle conservation of energy. Okay, so we can conclude that say if we heat up the kettle, so the electrical energy that we use to that we supply to the kettle is actually will be equals to the heat that we produce to heat up the water. So this one is a principle conservation of energy. So are you clear now about the specific heat capacity? Avinash, can you text me when you're free? Okay. Avinash, sorry, Avinash. Alright, so any question you want to ask teacher? So are you clear? Can you understand for chapter specific heat capacity? Alright. So never mind, I will give you the exercise later. I will assign in GC. So make sure you understand. So I will see whether you can understand or not. Right? Okay, based on your answer. Okay, so see you on, I think on next on Saturday. Don't forget on Saturday at 2 p.m. Okay, please submit your work for those who still didn't submit. Okay, no need for me to remind you all the time. And also for all the subject teacher, okay, I got some complaints that you didn't submit your work. So please, all right, I don't want to add all the teacher, okay, in the parents group. Okay, so let's live peacefully. Okay, so just do your work. Okay, so let's say if you need more time, you can discuss with your subject teacher. Okay, but make sure you did it. Okay, all right. So thank you, class. All right, so take care. Okay, bye.
Thanks, sure.
Bye.
Thank you,
Okay,
teacher.
welcome. Bye bye.